Welcome to Homework Lib.
Okay, so we're doing chapter 29, problem 69. So in this problem, we have this ramp beautifully drawn here, and is all wired bars, and we have one bar here of length L, big L, and is falling down, and this is all in a magnetic field pointing straight down. So as this falls down the ramp, there's a magnetic flux that is induced from the current going through that's completed circuit there. Okay, so we want to figure out some information about that current. So first we want to figure out which direction that current that is going to be induced in this circuit is going to be going. Does it flow from A to B in the rod or B to A in the rod? Okay, so first let's think about this in the frame of Lenz's law. So we have a phi B that is pointing downward with the direction of the magnetic field, and the area is decreasing. So that means this is decreasing. So to oppose that, we must need an induced magnetic field upwards. Oh, sorry, induced magnetic field downwards because that is decreasing. So if our induced magnetic field is downwards, we use the right-hand rule. Let's figure out which way that should go. So the right-hand rule should say to produce a downwards thing should be clockwise. So that means A to B. So current is clockwise, so we flow from A to B. Perfect. Okay, so for part B says, we let this rod fall down such that the only force it feels is the force of gravity and the magnetic force from the induced magnetic field. So we want to figure out what the terminal speed is. And the terminal speed basically tells us when the magnetic force of the rod is equal to the horizontal component of the normal force, which is normal times tangent effect phi, or mg tangent phi. So we want to figure out when the magnetic force is equal to that. So what is our expression for magnetic force? Well, it's the current times the length of the rod times the magnetic field. We can relate this even more in terms of EMF over the resistance. Let's keep going here. We can now write the EMF using Faraday's law as the time derivative in the magnetic flux. We know that the B is constant, so we can pull that out and say this is LB squared over R times the change in area with respect to time. And now, lastly, we know the change in area by just the horizontal component of the velocity that's shrinking the area, since it's always L times that horizontal component. So this, we can pull that L out, and we're left with L squared B squared over R. And this is V times cosine of phi to get the angle right. Cool. So now we have an expression where mg tangent theta equals v t, for this is our terminal speed, times L squared B squared over R cosine theta, or phi. So we can rearrange and solve for the terminal speed to be R mg tangent phi all over L squared B squared cosine phi. Awesome. That is it. So for part C, it says we want to find the current in it when we're at the terminal speed. Okay. So we know that the current was the EMF over the resistance, which is the same as the change in magnetic flux over the resistance. And that's the same as we saw before as B over the resistance times terminal speed times cosine of phi. So we can now plug in what the terminal speed is, and we're left with b over r cosine of phi times r mg tan phi over L squared B squared cos phi, and that all equals the current. So lastly, let's cancel some stuff out, and we see that we're left with mg tan phi all over LB. Awesome. Let's move on to part D. So part D is asking us for the power through the circuit, and we know that the power through the circuit is the current squared times the resistance. So we can easily just do that out from our current before. So we have resistance times m squared g squared tan squared phi over L squared B squared. Awesome. That's exactly what we wanted. And lastly, for part E, we want to find the power from the work that the gravitational force did on it. So the work the gravitational force did is Fv times the angle, which was cosine 90 minus phi. So if we put this out, we know that F was mg times the V terminal, and cosine 90 minus phi is the same as sine phi. Let's plug all this in. We're left with mg r mg tan phi over L squared B squared cos phi times sine phi. Okay, let's start simplifying. We see this r m squared g squared. Cosine over cosine is tangent, so we have two tangents all over L squared B squared, which is exactly what we got from part D. So we know this is working, and we did it correctly. Awesome.